So, good morning, everyone, and welcome to the 2021 Ultra-Mechatronic Circus and Demo Day. I'm Sam Cross. I'm manager for energy for Ultra Networking Platform, and we'll open the event today. Looking to the program, if we could go to the next slide, please. So the Mechatronic Circus today is the morning part of the event, where we present smart devices which are made by Ultra University students in the mechatronics courses. And then from 11 o'clock onwards, we move to the demo part of the event. This will be opened by Professor Kari Tammi, and here we will see presentations and demonstrations from our research groups presenting their latest research. We'll start there with a presentation on digital twin web by Juuso Autiosalo, before moving into two parallel sessions with demonstrations on different topics. Next slide, please. Just a word about the Q&A and chat functions during today's event. So please use the Q&A functions for questions to the speakers. That's using the little box you see at the bottom there with the two speech bubbles, and you can also upvote questions of other attendees there. Use the chat function, that's the one with the box with just a single bubble, if you need help from the organizers, have technical issues, and we'll also use the chat there to send links and other announcements. Next slide, please. So first I would like to hand over to Petri Kuusmanen for opening words, and Petri is a professor of mechatronics, and he's running the mechatronics project course together with senior university lecturer Ano Kiviluoma. And his research interests are in heavy machinery and recent also in hydraulic machines. In Mechatronic Circus, he will introduce 6 different student projects which cover different fields of mechatronics, from mobile robotics all the way to nanocellulose testing devices. So I would like to hand over to Petri for opening words. Please, Petri.
So, thank you, Sam. And as Sam mentioned, this Mechatronic Circus is end gala of a student project in mechatronics. The course is 10 credits and 12 weeks long. So we have started in the beginning of this year, and now students are ready to introduce the end products of the course. And if you wonder what's the circus, from where comes that name, the background is that about 10 years ago we started this end gala in this current form, and student proposed that why not to use circus name for this event, and from that we have been Mechatronic Circus, and today this is 11th time in this form, and unfortunately also second time in remote mode because of COVID situation. You may understand that during these 2 years, COVID has been limiting our activity a lot at the campus, and also this year this has been the case. Anyway, students have had limited access to lab facilities, and thanks to that, they have been able to build the devices which will be seen today. And I have to thank the students already now about hard work they have been doing in these circumstances. As mentioned, that this is Mechatronic Circus, we try to get the feeling of circus, and that's why we will start following the tradition with the circus performance, and it will be given by Sanni Sarlin. I hope that all of you try to grasp the atmosphere of circus during his presentation. Sanni, floor is yours. Wow, I was dreaming that I'm Sanni with her power and control muscles. Unfortunately, now it's over and it's time to come back to the Mechatronic Circus program, and we will start the student presentations, and the first case is such that if you have to move liquid from one place to another, and you should do it accurately, and you have very different viscosities in the liquid, how to do that. We have a student team, Alexander Björklund, Johanna Sipilän, and Joel Stening, who have solved this challenge, and the team is Rethink Beauty. Floor is yours.
Täällä on sitten pyörimässä. Joo. B-rollin. Kolmas ja 8.
Joo.
2.19.
Hi. So I'm Joel Stening, and you just saw the video describing what we've been doing in the lab related to our project. So hello once again. We are the team Rethink Beauty, and we wrote this scientific article, Accurate Dispensing of Liquids with Various Viscosities. And the video you just saw was some footage we got when making the measurements for this scientific paper. As you might see, this is our scientific setup. So we have three kinds of measurements. We have a weight measurement, then we have a time measurement for the pump, and then we have a flow meter or flow measurement. And the idea is that we would like to measure how much liquid we have, how much liquid has traveled from this container to this container. So you can see from the sheets here, we have a measurement for time, a measurement for weight, and then for a measurement for flow. And how we did this was that we measured the we did all these tests always for water, shampoo, conditioner, and then hand sanitizer. And for all of these different liquids, we did 3 points with 3 repetitions. How we verified that we have like how much we have been pumping was with a scale, which you might have seen in the video. And depending on the measurement, we had different methods of weighting the achieved results. On a quick look, we came to the conclusion that the best way to track the weight change or the liquid dispensed to a container like this is actually using the weight sensors. Thank you for listening and hope you found this interesting. If you have any questions, feel free to ask those. Thanks.
And thank you, Team Beauty. And now it's time for questions. So you can send the questions to Q&A tool or just to the chat or by any other means you can find. Panu will check if there is any smoke signals outside. Okay. So the first question is that in this an experimental setup to confirm a closed form solution to the flow weight relationship. Could the team answer to this question? So please, and you can put your videos on so that we can see the faces of the student team.
Hi, so yeah, I'm having a bit technical difficulties. This Q&A thing is quite complicated. But so I think someone like if the pump is empty and if the hose we have is empty. So what we did before all these experiments, we always pumped the hose full with the liquid we were going to pump. So that's how it didn't affect the measurements.
Okay.
Okay. And then I can see another question here. So it's from Shashin Kandu. And is this an experimental setup to confirm a closed form solution to the flow weight relationship? That's a good question. I think what the goal here was to compare these 3 methods of dispensing a liquid and then look at this EU directives which state how much a variation there should be in products like this where you dispense liquids, and all these methods were compared to that standard. So no, we were not looking like at a closed form solution, but more at how much and how accurately we could dispense liquids with these measurement systems.
Okay, thank you. And then we have in chat, we have also questions. First question is, how precise can the liquid, precisely the liquid can be transferred? So could you estimate what's the accuracy of the system?
Thanks for the question. Jonas and Alexander, do you guys have something for this? I think you were handling the data more than me, so.
Yeah, hello everyone. My name is Alexander Björklund, and I think I have some kind of question at least to or answer to the question. So from our results, we got that at least for time measurement, the most precise one was 0.3 milliliter, but I think that was quite an outlier. But for overall, the preciseness of the liquid transferred is within, let's say, a bit under 5 milliliters. Some liquids got a bit over, up to 10 and 20 milliliters as well. It depends on the liquid transferred and also quite a lot on the dispensing method used.
Okay, thank you. And the second question in the chat were that were the values in the Excel file obtained manually by just checking the weight scores, or did you have a sensor automating it?
Yeah, that's a good question. The values were obtained manually, so we weighted the container or the bottle where the dispensed liquid was put into, and then we put it into an Excel. So we didn't have a possibility, or we didn't automate it so that we would get a raw data directly from it. So it took maybe a bit more time than it would have if we were to automate it.
Okay, thank you for good answers. Is there any additional questions? If not, then thank you for the presentation. And the next presentation is dealing with load measurement and in crane environment, for example, there is a need for measuring what's the weight of the mass, and team Aku Hietala, Olli Partanen, and Pyong Nyang have done a project about elasto-magnetic load measurement. Floor is yours.
Hello, everyone. I'm very glad to be here with my team, Konecranes, to present to you about the final result of the project that we have done. I am Hong, the guy with the beard. My friend Ollie is the guy with the sunglasses, and Aku, our team lead, is the other one. Our project is supported by Konecranes, and we decided to call it Elasto-Magnetic Sensor for load measurement. Can you change to the next slide? The question you might have right now is why load measurement is so important. And it's not actually an obvious thing. Let me take an example to make it clear for you. In cargo industry, when we use the cranes to lift the containers, its lifespan is affected by the mass of the containers. In fact, the lifespan of the crane is reduced drastically when the load is too high. So we really want to know how much we lift. And when the cargoes are placed onto the ship, we want to distribute them evenly to both sides of the ship in order to keep the balance right. So that's why load measurement is very important. The current method that we use to measure the load is strain gauge. But in this project, we want to explore a new approach and principle to measure the load. Our main goal is to prove that the concept can be applied in the industry. But we also wish that the method can be developed further to achieve even more accuracy and certainty than the current one. And with that in mind, I want to go through the principle that we use in our experiment. As you can see in the figure, we have two coils, which we call the primary coil and the secondary coil. They are wound around a ferromagnetic core. It is very important that the material of the core is ferromagnetic. Otherwise, this won't work. The primary coil is connected to a power source. When we allow the current flow inside it, the core will be magnetized, and the voltage will be induced in the secondary coil. After the setup becomes stable, we apply force onto the core and observe the change in the voltage in the secondary coil. And from this, we can formalize a relationship between applied force and induced voltage. And so after we got the idea, the project steps become quite clear and simple. The picture on the left shows our first trial to see if the setup really worked, and it did. And the second one is the one that we actually used in our experiment. There's only one thing that I want to point out here is that we used the tensile bench to effectively apply and control the load onto the core. And now Oli will tell you more about the test that we did.
Yes, for testing our devices, we scaled it down a bit from the actual size of the crane hook, and we decided to use a 10 mm steel bar to mimic the hook shank that the sensor would be attached to. The sensing device was then wrapped around this core, and primary coil was excited using the signal generator and amplifier to act as a AC power source. For data acquisition, we used the high accuracy multimeters to measure excitation voltage and current for the primary coil and the induced voltage and its change in the secondary coil. Also, to counter the effect of the temperature change of the device during testing, we attached a thermocouple to measure surface temperature of the steel core. With the setup done, we mounted it to the tensile bench, and with that we were able to apply varying loads with high accuracy for the steel bar to study the effect of the stress to the induced voltage in the secondary coil.
Okay, so then here is a short video of testing in the laboratory. So in the setup we had audio amplifier and signal generator, which you can see here. And then here we have multimeters for primary and secondary coil voltage measurement, and the numbers are changing all the time, as you can see in the video. And here we have the multimeter for current measurements. And here you can see the temperature measurement with thermocouple, and that's connected to the multimeter down here. And here you can see increasing load curve from 10 kilonewtons to 12 kilonewtons. And that's the setup. Then about the results. So we expected the relationship between force and induced voltage to be linear, but it was not. So as you can see from the graph, we have force on the y-axis and change in the coil voltage on the x-axis, and the instead of linear relationship, the equation is quite well following this second order polynomial function. So here we have the maximum absolute error about 300 newtons, and the average error percentage is 5.6, and repeatability error 0.069%. Then conclusions. So proof of concept was successful because this EM sensor can be used in crane applications when the force voltage relationship remains the same for crane capacity area. And the setup we built, the accuracy was 94.4%, which means 10.4 kilograms on average error with loads from 0 to 1,200 kilograms. And on the right hand side, you can see the actual concept of our crane sensor. So here we have 40 millimeter crane hook shank, and the sensor is 75 millimeter long. it has 1000 rounds on primary coil and 200 rounds on secondary coil. And the hook material in this one is IC1040 carbon steel. And this kind of a setup needs approximately 90 amps to make the core saturated. Thank you for your attention, and if you have any questions, now it's time.
Yes, and now it's time for questions, and please send to Q&A tool or to chat the questions. Okay, there is one question in the chat. Did the temperature of the steel bar actually affect the measurement? And if so, how much did the temperature change? So could the team answer to this first question in the chat?
Yeah, that's a good question. Actually, the temperature is very much depending on the current we use. So we use different currents during our test, and the temperature varies like ±5 Celsius degrees, depending on the current.
Okay, then in the Q&A tool, there is a question. What kind of transient response do you see when applying full load? You answer to this question. So what kind of transient response do you see when applying full load? Did you test that kind of response?
Actually, I'm not quite sure what the transient response here means. So maybe can you please explain it a little bit?
Let's ask some definition for the question, and meanwhile we could take a question from Sven Bossut. Does the measurement still work if a permanent magnet is nearby? So does the permanent magnet have an effect on the measurement?
Yeah, thanks for the question. We didn't test that, but I would argue that it would affect the system, the permanent magnet, and if the system is calibrated when the permanent magnet is already nearby and the setup isn't changed, we think that it should be able to work.
Okay, thank you. The voice was a little bit low, but and actually now there is from Sakin Kundu, there is a defined question so that there must be some current or voltage surge before the system settles that might affect the material chosen, etc. So
yeah, thank you for the definition. I think this has something to do with the saturation of the magnetic field. So we needed to like first test what will be the saturation point of the core material, and for that to get it saturated, we need a certain amount of current into the primary coil. And yeah, that's of course depending on the material of the core. Olli or Hang, do you have anything to add into this question?
Not really. The core material only has to be ferromagnetic for this phenomenon to work at all.
We have some questions. Do you know the reason why the relation is not linear as expected? So it was slightly unlinear. Can you explain why?
Yeah, thank you for the question. That's actually the one which we have been working on for a couple of weeks now, and still no clear answer to that. But in some related articles, the load voltage relationship becomes linear when the forces are like very high, or let's say many thousands of kilonewtons, which is not usually the case in the crane applications. So now our best guess is that we just are not testing with high enough loads to get the linear dependency between those two.
Okay, and the next question is also about the magnetic fields. It's a little bit similar question as Sven Bossut had. So did you shield the sensor somehow against the external magnetic fields?
In our test, we did not shield it anyhow, but in real use cases, the external fields could become an issue and some shielding should be applied.
Okay, thank you. And then one question about temperature behavior. It's similar as earlier asked, but does the temperature have any effect to measurement? So could you still answer to that?
Yeah, thank you for that. So basically, when we used higher current, the temperature in the coil was increasing, which changes the resistance of the coil, and then we have lower induced voltage coming out from the coil. So that's the basic phenomena of that transistor.
Okay, thank you for questions and a good answer for the team, and maybe it's time to give a big hand to the team. And really, even though now we are making this Mechatronic Circus via Zoom, in a normal years, we used to have one-day event here at the campus, and we had up to 500 visitors from industry, auto campus, and also from high schools. So we had several school classes visiting us, and it was important for us that our future students visited this Mechatronic Circus. Maybe one reason for that success was that it was a pea soup available for everyone here. Unfortunately, we can't deliver pea soup via Zoom, at least not yet. Okay, next presentation will dealing with propulsion, and a challenge with the propulsion systems is that if you use them in different modes, the efficiency easily decreases. And team Jan Gregor, Alpo Kuusisto, and Janne Mattila have done research what happens in tunnel mode in an Azimuth thruster. So please.
Welcome. We would like to introduce you our work, which was improving tunnel mode efficiency of a combined azimuth raster. My name is Jan Gregor, and I would like to introduce you quickly what was our goal and what was our task. What is azimuth raster? Azimuth raster, with azimuth raster, ships make propulsion and steering, so you can manipulate with the ships basically. And combined azimuth raster, which is specific kind of thruster, has two operation mode: open water mode, which is used most of the time of the ships, and tunnel mode, when the thruster is retracting back and can be used in the shallow waters. The problem of current design is that the efficiency is good in the open water mode, but it's not satisfactory in the tunnel mode, especially in the reverse direction, because some flow is leaking in the bottom well, or there is circulation of the flow. We did a background research in the topic, and to understand better the behavior, we create a 2D simulation in two perpendicular planes. In the left side on the picture, you can see that in the horizontal plane, there is no problems at all. But on the right picture, in the vertical cut, you can see that there are some problematic places where the flow is leaking or is not as we would imagine, or there is some circulation. We did some improvements to the construction and use a combination of static structures and movable flap. The flap is open when the thruster is in the open water mode, and close the bottom well when the thruster is retracted back. And together with the static barriers makes the flow continuing and avoid the circulation or the other not wanted things, not things we wanted. We simulated the behavior of this with CFD simulations, and Jan is going to tell you something about that.
So, okay, here you can see the initial forward flow of the tunnel. It looks really good on this point. Some small circulation in the upper part, but then on the backward motion there is much more turbulent flow on the tunnel, and it circulates quite a lot. But here, when the same thruster and tunnel is closed underside and nothing else done, you can see what is really circulation around. So it circulates the flow and nothing more of going to the tunnel. And here you can see results forward, and we got some improvement, but it sucks quite a lot from underside. But the flow is going to the tunnel, and its efficiency is about 95% on this. But here we got some much better improvements to the backward flow, and now it's almost efficiency is 90% this way. It was in the initial, there was only 64%. So here you can see on the initial forward simulation and the final forward simulation. And this was a backward simulation, and it was really bad in the initial phase. You can see there is a circulation on the upper part, also quite a lot of turbulent flow on the tunnel to the upper part, and the final result was really good when there is even chamfer there. And here are the results. So the forward velocity was quite good, almost 90 in the initial phase, These blue ones are initials, and then we got some 5 cubic meter flow more on the forward velocity, and the reverse velocity we got much more, from 65 to 82. And Albo is continuing the tests of tunnel.
To validate the simulation results, we made a model in scale 1 to 20, cut from foam and epoxied. Model was driven by cordless drill, and we measured thrust and consumed electric power with sensors connected to Arduino. Thrust was measured with a strain gauge, current with a Hall effect-based sensor, and voltage with a voltage divider connection from battery to Arduino. Then from power consumption and thrust, we can calculate efficiency. Space needed for our setup was bigger than a cubic meter water tank, but the Aalto Marine Lab was closed due to pandemic, so we had to rig experiment set outside. It was pretty cold and windy in Otaranta, and due to technical difficulties, we did not get results to compare with simulation, but we did get some good experience in field tests. Team Tunnel Flow sends you warm greetings. Bye.
Thank you for the team, and thank you for cool presentation and cool greetings. Now it's time for questions, and while you are preparing questions, I could tell that this course actually doesn't totally end to this Mechatronic Circus, but we have still one activity. 27th of April, we will have a Baltic Mechatronic Symposium. Typically it's in Tallinn, and but this year it's also in remote mode. And there student teams will give a presentation of these research projects, and also the conference papers, 6-page long conference papers will be published in the conference proceedings. So in this Mechatronic project course, students both build the devices and write a conference article, which will be published. Okay, so there is some questions. First, any comments on the performance of the proposed solution in ice conditions? Cool question. How does this system work in ice conditions? Good team answer.
Hello, Alpo from Team Flow. We did not measure the system in ice conditions. The simulation was restricted to the area inside the tunnel and a little bit below it. Ice probably would not affect this system so much, as the ship is in the direction of the thrust from the tunnel. The ship is in practice stationary. Ship is not moving sideways very fast. And so ice is like a water surface anyway, so it doesn't really get into the tunnel, or the flow is not much affected by the ice inside the tunnel. That is our assumption, but we did not do simulation of it.
Then next question from Thomas Tienen. He understands that the rotation of the propeller was not modeled in this CFD simulation. How does the result change if this was included? So what's your feeling? What kind of effect propeller and its rotation would have been.
Okay, hi, here is Janne Mattila from the team. So that if we have made those propeller also to the simulation, I think that it would increase the efficiency of the tunnel as the flow is rotating then on the pipe. So it might rise a little bit that efficiency of the tunnel.
It would have a positive effect on efficiency. Then Raine Viitala is asking, was there a technical solution proposed on how to close the bottom? So could you a little bit explain about the technical solution, how to close the bottom?
Hello.
Yeah, continue, or I can continue. Yeah, there is like a proposed solution for that. It has two parts. Part of the bottom, which is like not in the way of the thruster when the thruster is going down into the open water mode, is closed just by a static barrier, and the rest there was modeled a flap, which is rotating by the hinge in one of the sides, so it can open and close together with the thruster. And the proposed solution was to use a hydraulic hinge actuator, because then it would be easy for us to lock it thanks to hydraulic, and because we need to resist quite a huge forces there from the water flow.
Okay. And then in the chat there is a question: what kind of help or guidance or support did Kongsberg provide? And just to tell the audience that these topics for these projects come from our research projects, which means that these are indirectly from the industry and also directly from the industry. So all the projects have some kind of connection to industry, and this project was and topic was provided by Kongsberg. But question to the team: that what kind of support you got from the company?
Thank you for the question. I have to thank Kongsberg because they were really active in this and providing nice support. Maybe the biggest support was that we had weekly meetings, which is kind of way to push us forward. So when we start weekly meetings from the beginning of the course, then we start to do work right away. And anytime we asked something, they would provide answers. And when our contacts in Kongsberg didn't have experience on, for example, model testing, then they contacted other people from Kongsberg Sweden that came to explain us about how the model testing works and what are the problems and complications they face. So we were provided all the information we asked, and pretty promptly.
Yeah. Yeah. So could you repeat what was the biggest modification that you made to the system to get the results?
We adjust the inside of the tunnel with barriers to make the flow in the right way we wanted. Basically, it was combination of some static barriers, which some of them were shaped in the cylindrical shape, some of them were just flat in the bottom wall, and the one rotatable flap, as we mentioned already, because we were considering during our project also using maybe some kind of water jets or another sources, but from the simulation we get that these quite simple adjustments, which are also easy to assemble to the ship, that was kind of key aspect for us also, makes quite huge improvement, and it's not necessary, it's easy and solution which gave us what we wanted.
Then next two questions, maybe we could combine these. Could the ocean water have affected the sensors in any way, causing the technical difficulties you experienced? And the second one, did you take into consideration the corrosion effect of the environment? So.
Thanks for the questions. Regarding the sensors, no, ocean water was not the problem. All our sensors were dry, high and dry above the water. The technical difficulties were mechanical, the attachment, torque attachment of the propeller, and then the traditional problem of not having enough time at the end of the course to repair this stuff and make repeated attempts. For the general corrosion environment, yes, we talk with Kongsberg about these hydraulic systems and how they should be arranged so that the corrosion does not affect the sliding parts or the parts that need to be watertight. These main parts of the system are, of course, they are thick steel and have the normal corrosion treatment like ship's hull. So there was some to consider about which way to orient the hydraulic cylinders so that the seawater would only contact the outer surface of the cylinders.
Okay, thank you for the team. And it was great to hear that the team was on a dry land back from the tests. Actually, now we are in the middle of the circus, and we will have a short break. So we'll come back at 10:10. So and please keep the circus mode on your feeling. See you. Would like to inform you that these student presentations will be on all the web pages next week, and all those who have registered to this circus will get an email and a link to that material. So you don't have to write down all the notes. Next presentation will be dealing with the future of paper making, and as everyone knows, Finland is country of forests and paper making, and nano paper is something which is very promising material, and Tuukka Virki and Paul Lim have done research how to dry nano paper. So floor is yours.
Hello and welcome to our presentation. We are the nanopaper team, Tuukka Virki and Paul Lim, and we're here to tell you about our project on nanopaper. We have been studying the effects of pressure and airflow on the drying rate of nanopaper, and we're doing this in collaboration with the Bioproduct Center of Aalto University. Let's start the presentation with some basics of the topic. Some of you might be wondering what nanopaper is. Well, to put it simply, nanopaper is just like normal paper, but built from smaller fibers. Paper is produced from a pulp that contains water and wood fibers. The paper sheet is formed by pressing water out of this pulp until there are only fibers left to form a sheet. Traditional paper is made from large fibers. With the nanopaper, though, the wood fibers are processed to nanoscale by grinding. So the fibers left in the pulp are much smaller than the normal paper fibers. When the water is pushed out of nanopulp, the paper that is left is much more dense. Many studies have been conducted on nanopaper recently. This is because researchers believe that nanopaper has great potential and many applications in different fields in the future. The reason we believe there is great potential in nanopaper is because of its unique properties. These properties include, for example, great tensile strength and conductivity. And as we can see on the picture on the right, nanopaper can also be transparent. With these properties, it could be used in various applications. It could, for example, be used to replace oil-based products like plastic packaging. There are also applications in electronics and biomedical field because of the conductivity and biodegradability. Nanopaper is also a sustainable material because the raw material can be obtained from agricultural waste. Okay, well, why are we not using this great potential and properties already? There are still many challenges in commercializing nanopaper. Because of the smaller fiber size compared to normal paper pulp, more energy is needed to dewater the pulp and dry nanopaper. Because of the energy consumption, the scalability of production is still not yet figured out, and the price of nanopaper is not on par with normal paper. The dewatering and drying process must be researched to enable commercial production at some point. And with this small introduction, we'll now move on to what we have been doing in our project.
As mentioned before, the project was done in collaboration with the Bioproduct Center of Aalto University, and our objective here was to see how pressure and airflow affected drying rate of the formed paper. To do this, the group had to design an airtight device that would be under pressure and possibly be exposed to boiling temperatures. It was also requested that the chambers would be transparent in order to see the process of paper forming more clearly. As for the device itself, it is rather modular, meaning we can add different sensors, change the filter plate, and add more components. This gives the device more value because building the device is only one step of our project. Gaining data on how nanopaper dries under pressure was the purpose of building the device. The modularity of the device allows us, for example, to research how temperature would affect the drying rate once the necessary sensors and components are added. The process is done in two phases. The first phase focuses on producing the paper sheet on top of the filter plate. This is done with the help of pressure, which forces the water from the upper chamber to the lower. The only thing left is the wet paper sheet on top of the filter plate. After the first phase, we remove the water from the bottom chamber, wipe the chambers, and weight the filter plate that holds the paper sheet and place it back. On the second phase, we increase the pressure and add a vacuum on the bottom chamber. This is also when we start taking measurements of pressure and airflow. The second phase is kept going for a couple of minutes before we turn off the pressure valve. After the second phase, we take the filter plate out and weight it again. The difference in weight tells us how much the paper dried. Next, we will show you a video that visualizes the first phase of our process.
All right, hi everyone. My name is Tuukka Virkki, and this is my colleague Po Lim. We're going to introduce you to our nanopaper process and the device. So here we have our nanopaper device, which we built. On the top here, we have our pressure regulator, our pressure sensor, our pulp, and our flanges that contain the filter plate, and on the bottom we have our draining system. So now we have our power supply connected to our pressure controller, and next my colleague is going to give out a signal to the controller, and we will increase the pressure inside of this chamber. This leads to the water going down to the next chamber and through the filter plate. When we increase the voltage, the controller allows us to have pressure in the first chamber. Next, we apply pressure to the chamber.
After all the water has drained, we can disconnect the middle flanges and take out the filter plate with the paper sheet.
This was the first step of our drying process, and in the end you could see the wet paper sheet that was formed. This wet paper sheet still needs to be dried, and that happens in the second phase with the help of increased pressure and airflow. In the video, we conducted a test run of the process with normal paper. For phase 2, we set the pressure to 2 bars, while the lower chamber valve was open. The paper dried completely in 5 minutes. Our future plans are to add an air heater so we can also study the effects of temperature of the drying process. And to give you the faces behind this project and presentation, here's a picture of our team. And here are the sources we use for the figures. Thank you, the audience, for taking your time to listen, and we would also like to thank the Aalto staff for helping us with the project.
Okay, and now it's time for questions for Tuukka and Paul. And please put your videos on when you answer to the question. So there was the first question is that what's the material of the transparent cylinders?
Yes, I can answer that question. Thank you. The material of the transparent cylinders is borosilicate glass. It's a type of glass that can sustain great temperatures, and it's a really tough glass.
Yep. So and just a comment, when I've been following your project, so that the delivery time of that kind of special components like this glass cylinders, it's a challenging part of 12-week course when you have to wait for components several weeks. Then there is a question about the energy consumption of drying of nanopaper compared to normal paper. What could be the big difference?
One of the studies we read said something about nanopaper drying in 1 to 4 hours, and the paper we used dried in 5. So I guess it can be like up to over 12 times if we just go based on time.
Yeah, so basically we don't have the results of the energy consumption, but that's something that's being studied at the moment at the Bioproduct Center in Aalto University. So I hope they'll get the answers soon.
And how about the drying time of nanopaper achievable with your setup? So you didn't do that yet, but what's your qualified guess for that?
Well, I don't know if Po is going to have an answer, but we've seen some studies that increasing this pressure will fasten the process. It will make it quicker, and the 4 hours drying rate or dewatering process was with only a vacuum, and I think the process might take from 40 minutes to 1 hour.
Yeah,
or
that
would
sounds
yeah
about right.
yeah
I'm also not sure that they add heat, since we can possibly go up to like 6 bars if necessary, but I don't think we want to do it because those are ultimately glass cylinders. You don't want to pressurize it that much.
There is, thank you. There is a question from Raine Viitala, who is interested that do you have ideas on how to make the drying process continuous or dewatering to be particular?
I guess he means that how can we combine phases 1 and phase 2, because now we have to stop the process after phase 1, which is when the water sheet forms. We take it out, we wait the filter plate. Technically, we could just not wait the filter plate, but then we don't know how much water it contains. So we'd need a moisture sensor. That way we could make it continuous. We also need a way to wipe the inner glass cylinders. Then it could be continuous.
Yeah, but if we take out the weighing process and
the wiping too.
Yeah, the wiping and the weighting in the middle, then yes, you could do the whole process with just adding the pressure and adding the temperature in the process. So it could be done in one go.
And if doing that, then we could say that it's a paper machine, actually.
Yeah.
It's a continuous process. Then there is a question about top candidate of usage for this kind of material. So what's your...
I guess for the nano paper, right?
Yeah.
Since sustainability is so big right now in the world, most research are looking to replace oil-based products such as plastic packages with something else, and that could possibly be nano paper because it's pretty rigid. The main problems of doing that, as said in the presentation, that it's not good when it's wet. Like, I think everybody knows what happens to paper when it becomes wet. It just loses its rigidity. And that is one of the big issues on why we're still not replacing plastic covers and plastic packages with nano paper.
Yeah, but there's so much study going on that it's impossible to say what's going to be the biggest application.
Next question is dealing with the strength of paper, and if you compare nano paper to the normal paper, so what's the effect of fibers which are much smaller? So in nano paper you have very small fibers, and so what kind of effect it has on the strength?
The tensile strength grows a lot. It can be comparable to steel at that point.
Yeah, with some modifications, and it depends on the process of how you make the nanopapers, and if you use some additional materials in the paper. So the best results have been like on par with steel, but it depends on the paper type.
Your answer is that the strength is very high, even though there is the fiber size is very small. So
yes.
So you maybe you feel that the bonds between the fibers are that strong anyway. Then it's a question about the effect of temperature on the drying process. Did you investigate that in your tests?
We haven't investigated that yet, but our mentor, who basically we're making this device for, is very sure that it has high impact on the growing rate.
So
That's
yeah,
why.
we have plans to add the temperature, the air heating, and temperature measurement, and we believe that it has a great impact on the drying rate.
Thank you for answers and putting your videos on so that we can see the faces of the future of Finland.
Thank you.
And big hand for the presentation. Now it's time to go forward and the challenge in this project was how to get industrial crane and robot platform to cooperate with each other. And team Alexander Schüssler and David Wark and Wang-Fu Cheng have done research on applying ultra-wideband localization system for crane robot cooperation. Floor is yours.
Hello, I hope this teaser video triggered your interest in our topic, and our topic is ultra-wideband localization for crane robot cooperation. Our team consists of myself, David, and Wang-Fu, and now we will show what our research project was about. Our outline is structured as followed. So we first start with the research problem, then we will describe our system, then we will describe what our experiment is about, then we will show the results, and then we will come to a conclusion. First, we come to our research problem. So with the rise of IoT and in industrial environment, more and more processes will be automated in manufacturing and logistics, and also the automation of material flow processes. However, in indoor environments, there is no access to global navigation satellite systems like GPS, for example. And therefore, ultra-wideband localization systems like the one we're using are a promising replacement for these GNSS. And the advantages of these systems are that they're relatively inexpensive, and after the system is installed in the environment, you only have to buy inexpensive tags that need to be localized for each robot. Another advantage is that you can retrofit these systems to older machines, and you can use commercial systems that are available, for example, the one we are using from Nokkala, and they are really easy to use and very simple. And therefore, we try to implement an ultra-wideband localization system for the cooperation between cranes and robots. And here you can see the overview of our system. So our system has three components. We have the ultra-wideband localization system, which consists of 4 beacons on the ceiling in the laboratory and 2 tags, one for the robot and one for the crane. And then we have a wheeled robot platform and an overhead crane. Now we come to our ultra-wideband system. And this is the only sensor we will use to control the robot. And we will use, or we used, a commercially available system from Nokkala, which is a Finnish company. And the system consists of beacons that you saw in the video already, that are on top on the ceiling, and tags that are placed on the robot and the crane. And this system measures the time of flight between an ultra-wideband signal that comes from the beacon, that will be reflected from the tags and goes back to the beacon. And this time of flight, with this measurement, you can calculate the position of the robot and the crane. The measurement data of these beacons will be sent to the Nokkala cloud, where we can retrieve the data and do our calculations and our control. And this all works in real time. Now we come to our robot. We used a wheeled robot platform, which is quite simple. And for our high-level control, we used a Raspberry Pi. And for our low-level motor control, we used an Arduino. And the robot has 2 motors for each side. Our control software is based on the robot operating system, which is the most popular software frameworks for robots right now. ROS code consists of nodes, which are, in our case, Python code. And these nodes are published or subscribed to different topics, which are messages between the nodes. And these nodes are, for example, sensors or motors or a control algorithm. For the ultra-wideband sensor, we have a WebSocket, which retrieves the measurement data from the Nokkala server. And this code also does some filtering with an average of 10 samples to get a more accurate data. Then the navigation node subscribed to the location data and uses this to control the robot. We used a really simple control algorithm, which has 3 modes, either forward, stopping, or backwards. And these modes are dependent on the location difference between the crane and the robot. So if the crane is in front of the robot will drive forwards. If it's under the crane, then it will stop. And if the robot is in front of the crane, it goes backwards. And then this navigation node will send PWM commands, which are the motor commands, to the Arduino, which then controls the motors. Now we're coming to our experiment. So we are doing a one-dimensional following situation between a robot and a crane. And the first step is that the crane is moved by an operator. Then the robot follows the crane is stopped, and then the robot should also stop under the crane. Then the crane is moved back to the starting position, and the robot should also follow to the starting position. Here you can see our results. So the results show on the y-axis the x-coordinate in millimeters, and on the x-axis we have the time in seconds. And this graph shows 5 periods, so 5 cycles of our experiment. And the blue graph is the robot, and the orange graph represents the location of the crane. And with this diagram, you can see that there's a slight delay of the robot before it follows the crane. So the crane starts, and then with a slight delay, the robot will follow. And you can also see that the robot overshoots a bit before it stops. And this is mostly due to our control algorithm, which is really simple and easy. And it also, this control algorithm also has some tolerances, which means that it's never completely under the crane, maybe, but more in a radius that we defined, that we say this is still acceptable to be under the crane. In conclusion, our experiment results show that an ultra-wideband system can be used to automate material flow processes. For example, our process of a robot-crane interaction, and a slight delay and overshoot of the robot due to primitive control and filtering algorithm is still there. And for future research, we should improve the control and filtering algorithm to decrease the delay and the overshoot. And we should also increase the complexity of our cooperation process. So for example, we could do a two-dimensional following situation. It would be harder, but it would be more realistic. And in the end, it would be good that there's a case study in a real manufacturing or logistics environment and not just in the laboratory. In the end, we want to thank the team of Nocula for providing us the system and for their amazing support throughout the whole project. And we would also like to thank Nilosha and Risto, our supervisors, and our teachers, Petri and Panu. And we want to thank you for your attention.
Okay, thank you for the team. And now it's time for some questions. While you are preparing the questions, I could mention that also next year we will have this Mechatronic project course, and if the companies or our other stakeholders, if you have good topics for this kind of student projects, we are very happy to get your proposals for next year, and hopefully we can have this in live mode with PSUP next year. There are several questions. First question is, what happens if there is an obstacle in the path of the robot?
So hello, and there's with our current robot, there's no obstacle avoidance, but it's due to the modularity of the code. It's really easy to just add 2D LiDAR or another sensor to avoid obstacles. So this is really easy to add to our system.
So for the students who are answering, please put the camera on if possible. Then there is other questions. Why there are any metallic? Was there any metallic obstacles like shelves or milling machines, etc., in the space where you did those tests? So that signal would be blocked from the robot to beacon. So could you answer what kind of effect that kind of obstacles could have for the signal?
We didn't investigate this phenomenon, but we did our tests in the laboratory, and there are different metallic objects, and we didn't see any effects. And the crane obviously also consists of metal, but there has to be probably a bit more further investigations.
Then next question is about how to make money with this project. So money is in mind of Jari Vepsäläinen. He's asking what kind of application could be the easiest for this kind of technology. So have you any ideas for that?
For example, in factories, when we have big metal objects that need to be moved, or even with small trolleys that are part of the material flow or of the manufacturing, if you put a tag on, you can spot where it is, and then you can analyze the movement and also automate the movement of these systems. So it's all about the automation of the material flow or other manufacturing process.
Thank you. Then there is a question, what about if the network connection is dropped midway?
So the system is dependent on working internet connection. So then there has to be a stop mode, maybe if the internet connection would be lost. So it's dependent on a working network connection.
Then a question about, did you notice any dead angles and or reflections for UVB from metal when conducting the laboratorium tests?
We didn't see any effects, but we also didn't investigate it further. So in our test, there were no problems, but we should investigate it further for the metal reflections.
And the last question deals with where is the global reference frame with respect to this, with the time flight transforms are performed? So
during the installation of the system, so the wall are always 0, and then you have to do measurements in the laboratory to measure the distance and where the beacons are located, and then you have the reference frame compared to the beacons. So you have to do measurements during the installation of the system.
Okay. So thank you for questions. I think there are in the chat there are some questions, but time is running, and I think we have to go forward. Big hands for the team. And the final presentation of this Mechatronic Circus will be dealing with actually paper machinery and other heavy machinery. And team Kalle Kinnunen, Alvari Seppänen, and Thomas Turin have built coupling with adjustable stiffness. So floor is yours.
Good morning, everybody. I'm Tommaso Turrin, and now I will introduce you to our project called Coupling with Adjustable Torsional Stiffness. To well understand the meaning of our project, I should start to make clear the meaning of these two words, coupling and torsional stiffness. Coupling are mechanical components used to connect two shafts in order to transmit power. You can see some examples here in the picture. Here you can see two examples, for example, of two different systems where we can find uncoupling. And here is an example of a typical coupling that we can find in those systems. While torsional stiffness can be understood watching the second image and following the graph. As more torque is applied to the shaft, as more angular displacement we will have on it. The slope of the graph is its torsional stiffness. The torsional stiffness can be also represented here as a formula. The image is explained in the same concept that I've already explained. But how are these two concepts related to each other? Well, these systems have to run in wide frequency ranges, and resonance must be taken into account. Resonance occurs when the frequency of an applied periodical force is equal or close to the natural frequency of the systems. Here we have a video where you can directly see the consequences of having a system in resonance, so the torsional vibration of the system are getting higher and higher until reaching the breaking point of the helicopter in this case. So why do we need a coupling with adjustable stiffness? Here we can see the simple natural frequency formula depending on mass and stiffness of the systems. Since we can't change the mass of it, the goal was to find a way to change its stiffness, obtaining variation of natural frequencies of the system. Knowing the definition of resonance, we know that changing the natural frequency of the system, we can so avoid the phenomenon of resonance.
Okay, next is the coupling design. The goal of the project was to design, manufacture and test a coupling which would have an adjustable torsional stiffness. We designed two different couplings. First one on the top right is beam coupling, where beams are used to adjust the torsional stiffness, and lower right is the spring coupling, which uses springs to adjust the stiffness. In the end, beam coupling was chosen to be manufactured and tested. Okay, let's go over some parts of the coupling. First we have the input half where the motor is attached. Then you have beams and the adjustable flange. Then we have middle shaft and the output half. On the left you can see a section view of the coupling. The coupling works when we attach a motor on the input half. The torque gets transferred to the beams to the adjustable flange. From the flange it goes through middle shaft, which is fixed on the output end, and the output half transfers the torque to the rotor. The stiffness of the coupling is adjusted by changing this effective length of these beams. On the bottom right you can see a typical cantilever beam. The effective length is the distance between the clamp and the force. When we increase this distance, the beam starts to bend more. We are basically using the same principle in our coupling. The effective length is the distance between the input half and the adjustable flange. Basically, we are moving the adjustable flange to change the stiffness. The middle shaft is fixed on this end, so when we are moving the flange to the right side, the effective length increases, so the stiffness decreases. And when we're moving this adjustable flange to the left side, the effective length decreases and the stiffness increases. The manufacturing was done in Aalto University lab. On the left you can see the milling of the input half. On the middle you can see threads being made to the output half, and to the right side you can see the cover of the coupling being made. Here we have a couple of pictures of the manufactured coupling. On the left you can see the coupling assembled and ready. On the right you can see the coupling installed into the Aalto University rotor lab test bench.
We tested the stiffness by attaching the coupling to a lathe. This side of the coupling is fixed, so it cannot rotate. This side can rotate, and we measure the displacement here. From this displacement value we can get the rotation angle of this side of the coupling. We exert torque here with this wrench, and there's a weight hanging out of it. From this display we can read the torque values. We obtained stiffness versus central disk position curve. On the y-axis we have the stiffness, on the x-axis we have the central disk position. Here with black stars we have the experimental data. As we can see, we get a good range of stiffness. We get higher and lower values compared to the previous coupling that was used in this application. Analytical and simulation had a much higher stiffness values because they didn't take account these plastic parts here which have a low stiffness. In the future, we could measure how the stiffness affects on the natural frequencies of this kind of system where the coupling is attached to a motor and a rotor.
So thank you for the presentation for the team, and now it's time for questions. So really today we have had six presentations and even very lively ones. And while you are preparing questions, I would like to invite you to the Mechatronic Circus 2022 about at the same time of April next year. And yeah, there is 2 questions. Do you have plans for on-the-fly adjustment of stiffness, and would such option be useful? Good question.
Yes. Good morning. I'm Tommaso Turin. Yes. The plan is basically to at the beginning was to obtain an adjustable stiffness like continuously, but one of the goals was to obtain the adjustable stiffness not using any electrical circuit. So one of the next goal would be studying a way to adjust the stiffness continuously without using it, like electrical circuit. There are several ways. We thought about them, but the time was the time that we had. So adjusting the stiffness manually, as you have seen in the video, was still a good result.
And then there are several questions about how to, about the same topic, how to adjust the stiffness while rotor is rotating, and also how to what's the stiffness compared to standard coupling, so fixed coupling. Could you answer to that as well? Do you feel that is the coupling as stiff as fixed coupling?
The coupling, the coupling that we have now is covering experimentally a range between 6,000 to around 50,000, the maximum level of stiffness. And as you can see, it's really changing. So we can obtain a pretty huge range of stiffness. And, you know, we had like, we have been studying, like we have been designing our stiffness, like taking as an example of the coupling that we already have implemented in our motor and rotor lab. So the goal was like to achieve a stiffness that could have been like higher and also lower. So the design that we choose was like to obtain these kind of values. Obviously, with other kind of design materials and citral level of stiffness, also like improving the plastic part that we talk about, we can also obtain highest value of stiffness. So that might be also another goal for the next studies. Thank you.
Question, what was the most difficult part of this project? You have built a real size device, so could you answer to that?
Yeah, for me, I would say that the most difficult part was actually obtain a manufacturing coupling, like manufacturing the coupling, like and obtain the result into it. We had some problems in the manufacturing. You know, we had to design the coupling beforehand, knowing the manufacturing problem. That's what I would say. Then I don't know if my mate wanted to add something.
Then final question, why did you choose this design? There was also design using springs. How would you answer to this question?
Yes, the main reason was that this kind of design is maybe more interesting to study, and so obtaining an adjustable stiffness continuously, while the spring design was maybe easier to manufacture, but not as interesting as the other in the following study.
Okay, thank you for a good presentation. So we have heard 6 presentations today, and hopefully you have been happy with these student projects, and really next year we will continue with new projects, new students. With these words, I declare this Mechatronic Circus 2021 closed. And our program will continue at 11 o'clock sharp with the after 2 minutes, and it will be introduced different research projects. So the demo day part will start at 11 o'clock. So thank you and bye-bye.